This is VLSI data conversion circuits, lecture 8. In the last class we were looking at ways of making this sampling switch linear. In other words, the device that we are familiar with, which can be used as a switch dependent on an external control signal, is the MOS transistor. This input voltage needs to be sampled and held on this sampling capacitor, and the basic idea is during the sample phase the switch is turned on by connecting this to a high voltage, and when you want to hold the voltage you just turn the switch off so that the input is sampled on the capacitor. And we were looking at the various non-idealities that could happen during this whole process, and one thing that was responsible for distortion was the variation of the resistance of the switch. And why does the resistance of the switch vary? If, as we are normally used to, we connect this voltage to VDD during the sample phase or during the track phase, the MOS transistor has a resistance which unfortunately depends on VGS minus VT. Now the VGS of this transistor, so during the sample phase the VGS is nothing but VDD minus Vin. So the gate over drive is VGS minus VT, which is VDD minus Vin minus VT, and the resistance of the switch therefore is given by 1 over mu n Cox W by L times VGS minus VT. For the time being we neglect the fact that VT is also modulated by the input voltage through the body effect, right. So when we were discussing this the last time around, we said that there is a fix for this, and the fix is actually quite straightforward. When you look at the expression, you see that the problem of distortion is occurring because the resistance of the switch is getting modulated by the input signal. So the fix to this problem is to prevent the resistance from getting modulated by the input signal. And how would you prevent the resistance from getting modulated by the input signal? The culprit is this character. So we see that the gate is being held at a fixed voltage VDD in order to turn it on, right. Unfortunately the source voltage is the input voltage and is varying with time. Therefore if the gate is held at a fixed potential in order to turn the device on, VGS is varying. So this suggests the solution of, we do not want to keep the voltage of the gate at a fixed potential, we want, on the other hand, we want VGS to be constant, not VG, right. So basically in the sample phase what we would want is to keep VGS fixed, which is accomplished in principle by putting a battery of value VDD between the gate and the source. This way the absolute potential of the gate will be what? It will be Vin plus VDD, which means that the gate source voltage is simply VDD, quite independent of the signal V. This way the resistance of the transistor or of the switch becomes independent of the input signal, and therefore nonlinearity is avoided. We have seen expressions earlier for the second and third harmonic distortion where the resistance varies as a function of the input signal, right. And the strategy used here, which seems to make sense, is to say the problem is coming because the resistance is varying with the signal. So in order to solve the problem, you make sure that the resistance of the switch remains constant independent of the signal. And how do you keep the resistance of the switch independent of the signal? When the source moves, the source is connected to the input, the gate also moves by exactly the same amount, right, thereby VGS remains a constant. Again, I would like to bring to your attention that in this analysis we have neglected the small variation of the Vt with respect to the source voltage, right. And of course, in the hold phase we would like to turn the switch off, and that is done in quite a straightforward manner. Right. Now, the next question is, how would we implement this battery? This is what we were looking at the last time around, and we said that one important thing that one must observe regarding this battery is that there is very little current being drawn from the battery, right. And further, this battery is only needed in one phase. So, during the sample phase, during the other phase the battery is not really required. So, from our prior experience in the analog circuits class, a capacitor which is charged to a voltage VDD is indistinguishable from a battery of the same voltage, provided you do not draw any current from it, okay. And this is particularly convenient because here we need the battery only for one phase, which means that even if the capacitor loses charge, it can be replenished in the next phase. For simplicity, I am just going to call the sample phase phi 1 and the hold phase phi 2, and so the in principle diagram of the switch will look something like this. During phi 1, this capacitor C bat is connected between the gate and source of the sampling switch. During phi 2, what do we want to do? We want to connect C bat across a voltage source of value VDD, all right. And what do we do to the gate of the sampling switch during phi 2? Must be connected to ground. All right. Now, the question is, how do we implement these switches? So, we have 5 switches in all, which also need to be implemented with transistors. And let us just quickly recall that if we want to have a switch which has to be turned on during any phase phi, there are at least 3 ways of doing it, right. One is to use an Nmos transistor whose gate is clocked at phi. Another one is to use a PFET whose gate is clocked with phi bar, and the third one is to use a combination of the two, also called the transmission gate. Let us also quickly remind ourselves where each one of these possibilities make sense. So, when would you like to use switch number 1, which is the NMOS transistor clocked with phi? It makes sense to use when, I mean, after all, you are trying to equalize these two voltages, right. So, an NMOS transistor makes sense when Vx is very low, typically close to ground. On the other hand, a PMOS transistor makes sense when the voltages you are trying to equalize are both high or both close to VDD. In several circumstances, you have a situation where the voltages that you at the two ends of the switch can vary from all the way from low to high. I mean, a classic case in point is the R very input signal, right, which can in principle take on different values as a function of time, in which case it makes sense to use a transmission gate. Is this clear? Okay. Now, let us start with the switches. So, what would you do for this switch? There, great, it makes sense to use an NMOS transistor clocked with phi 2, all right. What about this switch? Here it makes sense to use a transmission gate simply because the input can vary all the way from 0 to VDD, maybe not all the way from 0 to all the way to VDD, but sufficiently close enough. So, instead of this we have a transmission gate. So, where will the gate of the NMOS transistor go in the transmission gate? Phi 1. What about the gate of the PMOS? Phi 1 bar. All right. What about this switch here? That is also an NMOS transistor. Where does the gate go? Phi 2. What about this is a difficult switch. Let's start with this. Where do you think that switch will go? How do you implement that? We don't know. We go through all the three possibilities, see which works, right. So, let us see if the NMOS switch works there. Can I have any comments? What do you think? No? Why? So, clearly the minimum value of this voltage is VDD. Please note that this battery capacitor C bat is charged to VDD. So, the minimum value of the top plate of that capacitor is at VDD, right. So, clearly it does not make sense to use an NMOS transistor, which also means that the transmission gate must be removed from the picture, because if the NMOS is not doing anything, even if you put it along with the PMOS, it is not doing anything, right, which means that if the NMOS is out of question, it must also follow that the transmission gate is out of question. The only possibility left seems to be the PMOS transistor, and definitely the voltage is high. So, it seems like a PMOS transistor will help. Now, so let us now replace this with a PMOS transistor and see if it indeed works as expected. And this must be clocked with phi 1 bar, that is correct. Okay. Now, a PMOS transistor has 4 terminals, right, the 4th terminal being the body. And what do we know about the body terminal? What should we do with its potential? the body terminal of the PMOS transistor must always be connected to the highest possible potential that the transistor is exposed to. And which is the highest possible potential that the transistor is exposed to? Pardon? So, this voltage is VDD plus Vn, this voltage is either VDD plus Vn or ground, right. So, which do you think, where do you think you would connect the body? So, you will, good, so you will connect it to the left side, right. Please note that this is somewhat of a departure from normal practice. Normally in digital circuits, what would you do? You would, without thinking, simply connect the body of the PMOS transistor to VDD, right, and the body of the Nmos transistors. In many technologies you do not have any choice at all, it is automatically ground, right. And why do you normally connect the body of the PMOS transistor to VDD? Because you expect that no node voltage inside the circuit exceeds VDD. So, VDD is a safe place to tie the body of the PMOS transistor. In this case, however, clearly the potential of this node exceeds VDD. So, you cannot simply tie the body of the PMOS transistor to VDD, right. You need to tie it to the highest potential that the transistor is likely to see, and in this particular case that happens to be VDD plus Vn, and quite luckily in fact this potential always occurs at the same node on the left side. You understand? Okay. It turns out, as we will see going forward, that we will not be so lucky with the last switch, which is the one highlighted in green. So, what do you think we should use for this switch? Again, the answer is not immediately apparent, right. We go through what we know, which are these three switches. If one of them works, it is fine, we are done. If none of them work, we figure out what to do, right. So, let us start with the pure Nmos. How many votes for the pure Nmos? No takers? Okay. Why? The potential is too high. So, Nmos is not helping. If the Nmos is not helping, the transmission gate can hardly be used, right. So, it seems like PMOS is the only candidate which even remotely fits the job description, right. So, okay, now let us try and see if PMOS works. And what would you connect the gate to? Phi 2 bar, right. Okay. Now, there is the fourth terminal called the body, and we need to figure out where to tie the body. The body must be tied to the highest potential that this transistor is ever likely to see. Okay. So, can you now comment on what that highest potential will be? So, clearly this voltage here is going to be V in plus VDD, simply because the battery C bat has been charged to VDD in a previous cycle. So, one would therefore conclude that a reasonable strategy would be to simply connect the body of the PMOS transistor to the highest potential, namely this. However, if you think about it carefully, there is a problem due to the following. So, this voltage is V in plus VDD. When this switch here is supposed to be off, how would the terminal voltages look like? One terminal would be at VDD. I am simply redrawing this switch to focus exclusively on this. To turn it off, one would normally connect the gate to VDD, and this node would be at Vin plus VDD. Since Vin plus VDD is indeed the highest potential that any of these terminals will see, it is quite legal to connect the body of the transistor to Vin plus VDD. Unfortunately, however, while we are interested in keeping the various junctions reverse biased, we are also interested in making sure that there is no drain current at all. Unfortunately, as we can see here, this is not true, because this potential is Vin plus VDD, and these two potentials are at VDD each, which is equivalent to having the transistor operate in the saturation region with the source gate voltage of Vin. So, this is Vin plus VDD, this is VDD, and this is VDD, which therefore means that when the switch is supposed to be off, it will actually start to remove current from C bat, because C bat is connected here and is at a potential Vin plus VDD, and because this transistor is in saturation now, we see that this will draw away current, which is, and the current is given by 1/2 mu p C aux W by L times Vin minus Vt P the whole square. And this is completely undesirable, because you want the battery to hold on to that voltage VDD without losing that voltage, and therefore, using a PMOS switch here is also not a permissible solution. So, we now need to figure out what to do, because it seems as if the various switches we know, namely the Nmos transistor, the PMOS transistor, or the pass gate, none of them are suitable for use in this situation.
So, now let us the stuff that we have, the 3 switches that we have do not work. So, let us now go back to one of the switches and see what can be done to make it work. You understand? So, let us recall, for the Nmos switch, if this is Vx, the minimum voltage required to make this turn on is what? I mean, it is Vx plus Vt, but if you want a good switch, we normally are used to the fact that this Vgs is VDD, right. So, in other words, if this was ground, if Vx was 0, the gate would be connected to VDD in order to make it a, within quotes, good switch. Now, if Vx is not 0, but something higher, but you want to make the switch just as good, what do you think you should do to the gate? I mean, it seems like if VDD was good enough for Vx equal to 0, right, then if Vx was non-zero, what I would apply at the gate would be the non-zero voltage plus a VDD. So, in a similar fashion, if you want to turn off the switch, if Vx was 0, what would you connect the gate to? Normally you would connect it to ground. Now, if this Vx was non-zero, what do you think you could do? You could have connected to either to ground, or you could connect it to Vx. In other words, you do not need to connect it to ground where the gate source voltage will become negative, right. A VGS of 0 is good enough to turn the switch off, correct. In other words, if Vx is non-zero, then this will work just as well as a regular Nmos switch would have worked at Vx equal to 0 if instead of applying phi at the gate where phi goes from 0 to VDD, I apply phi plus Vx, right. In other words, earlier Vx was 0 and phi would go from 0 to VDD with Vx being 0. Now, if Vx is non-zero, something which definitely works is adding that same non-zero component to phi. Does it make sense? So, this is phi and this is VDD plus, right. Okay. Now, let us focus therefore, armed with this information, let us focus on this switch. So, Vx is now the two potentials that we want to make the same are VDD, correct. So, what should happen to the gate based on our discussion just now? Instead of having phi 2, what should we do? We must have phi 2 plus VDD, all right. So, the next question is, how would you generate phi 2 plus VDD? Okay. So, let us say you have a clock phi and you are faced with the general problem of generating phi plus VDD. What would you do? I mean, in principle, what would you do? So, if you have phi, then to generate phi plus VDD, if I had a voltage source of value VDD or a battery charge of value VDD, this voltage will simply be phi plus VDD, correct. Now, we resort to the usual trick of how do we implement the battery, correct. What do we do? What do you think we can do? The usual thing of taking a capacitor, charge it to VDD, right. And so, if there was a capacitor and this end was tied to phi, when phi was 0, right, when phi is 0 or when phi is low, the capacitor must be charged to VDD. So, how will you charge this? Okay. And by with what signal must the gate be controlled? When phi is low, this switch must be open or closed? Closed. So, it means that it must be controlled by, it must be high, it must be closed when phi is low, which means that it must be controlled by phi bar. However, please note that we are faced with the same problem all over again, right, because this switch needs to equalize two nodes with voltage VDD. So, in other words, this must need phi bar plus VDD, correct. We tried to generate phi plus VDD and then we found that, or rather we are finding that in order to generate phi plus VDD, we need phi bar plus VDD. So, then you say, okay, let me try and generate if I had instead tried to generate phi bar plus VDD, I would have needed phi plus VDD. You understand? This is a situation where I have phi, but I need phi bar plus VDD, right. Now, if I imagine that I needed phi bar plus VDD, then what would I have to do? I put phi bar here and this switch would be controlled by phi plus VDD, and this would give me what signal? Phi plus VDD, and this would give me phi bar plus VDD. So, now putting 2 and 2 together, what do you think we can do? The circuit on the left has got something, but needs the complement. The circuit on the right has got the complement, but needs phi plus VDD. So, now if you now marry these two circuits together, right, hopefully we will be able to get both phi plus VDD and phi bar plus VDD, and that is precisely what we are going to do. And this is phi. To generate phi bar, it is straightforward, you just put an inverter, correct. Does it make sense? And let us kind of quickly trace the circuit and see what happens. When phi is 0, what is the absolute voltage at the output of this inverter? It is VDD. Let us assume both the capacitors are initially uncharged. So, what is the voltage at the top plate of the left capacitor? It is 0, right. What happens to the voltage at this point? The capacitor is uncharged, so this absolute potential will be VDD. Now, consider this transistor, the gate is at VDD, the drain is at VDD. So, what will eventually happen to this capacitor? What will that potential eventually reach? It will reach VDD minus VT. It will not go to VDD, because the transistor will turn off the moment it goes to VDD minus VT. Okay. Now, the state of phi has changed, it has gone to from 0 to 1, which means the absolute voltage has gone to VDD. What is the absolute voltage at the output of the inverter? 0. What is the absolute voltage at the top plate of the left capacitor? It is 2 VDD minus VT. Now, if this is 2 VDD minus VT, that means this potential is 2 VDD minus VT. What happens to this potential now? It will get charged to VDD, because the gate is at 2 VDD minus VT, the drain is at VDD, right. So, the source will become VDD, and so this capacitor has now gotten charged to, the lower plate is at ground, the upper plate is at VDD. So, this capacitor has gotten charged to VDD, right. Now, if this is VDD, in the next phase what happens to this gate? It goes to 2 VDD, which means what happens to this potential? this gets charged to VDD, correct. So, now we see that both the capacitors are charged to, once you run this for a couple of cycles, we see that both these capacitors are charged to VDD, and therefore, this waveform will be what? Is that 5 plus VDD or 5 bar plus VDD? It is 5 plus VDD, and what is this waveform? 5 bar plus VDD. Okay. As you can see, the solution is not a very obvious solution. Right. In fact, it's a very elegant circuit, right, which is not at all immediately obvious, and this is part of what is called a Nakagome charge pump. Labeled obviously after the inventor. This was originally discovered or invented for use in DRAMs, where apparently high voltage is needed, and if 5 and 5 bar are complementary, then by muxing between 5 bar plus VDD and 5 plus VDD, you can generate a constant potential of value to VDD, right. So, this can be in principle used as a, by appropriate muxing between 5 plus VDD and 5 bar plus VDD, used as a voltage doubler which doubles the supply. Okay. So, anyway, that is not the focus in this course at least. So, what we do is therefore,
is there any feedback kind of analysis available for Nakagome transform?
there is no, I mean there is no feedback here.
I mean, since there is a loop which gets formed.
Well, once the capacitors are charged, this loop is not pretty much not doing anything, right. The only thing that happens is that once, I mean, because of the PN junctions at the source and source here and here, there will be a very slow leakage of charge, right, and all that is happening is that charge is getting replenished every cycle. So, once after a couple of cycles the capacitors are charged to VDD, there is pretty much, you can almost think of it as batteries which are just holding VDD. Okay. Well, not quite, because if you go through the same analysis that we did before, if the capacitors were charged to a negative voltage, then in the first cycle, one will come up to VDD minus VT, the other one, right.
Top plate of capacitors go to the gate of VGS.
Right. So after 1 or 2 cycles, it will simply settle to the right voltage. Okay. All right. So now that we have established this, then it is straightforward. So one uses the level shifted clocks to go and clock that switch. Okay. Now the last thing that needs to be done to make this work is what? What do we know about phi 1 and phi 2? You want to make sure that when these switches are on, these switches are off, and vice versa. So, it is extremely important for phi 1 and phi 2 both not to be active at the same time, right. So, in other words, phi 1 and phi 2 must not overlap. Of course, one can say I will have a chip and then it is your business to send me the non overlapping clocks, okay, but that is hardly an idea that will fly. What you want to do is to take a clock and internally generate the two non overlapping clocks, you understand. So, how would you take a clock and generate? So, in other words, the problem is this: you have a clock, from this you need to generate two clocks, phi 1 and phi 2, which are non overlapping, okay. And of course, using standard state diagrams, it is possible to derive the circuit from scratch, right. This is an asynchronous circuit, okay. At this point I will not do that, I will just quickly show you the core of the circuit and analyze it and show you that it works. And those of you interested can actually go and see how we can come up with the circuit from first principles. So, the core of the circuit is an RS latch made with NAND gates, for argument's sake, let us assume that the inverter is delay free, but the two NAND gates have delays Td which are deliberately made large, okay. Why do you want to make them, why do you think we would want to make them deliberately large? We need to have a control over the non overlap time between phi 1 and phi 2, right. If all gates are delay free, clearly you have no knob to turn at all, you understand. So, as I will show you in a couple of minutes, this Td is a parameter which controls the amount of dead time between phi 1 going low and phi 2 going high, okay. So, let us quickly analyze this circuit. Before we get into the transient part, let us see what happens in for steady state. If this is 0 and has been 0 for a long time, what will be the logic value here at the output of the inverter? This will be a logical 1. If this is a logical 1, what will be the output of the lower NAND gate? Pardon? This will be 0 and this will be 1. Is this clear to everybody? So, if this is 0, then this has to be 1, correct. If this is 1 and this is 1, this has got to be 0. I mean, please note that there is a positive feedback loop here, correct. Okay. Now, if this changes to 1 and remains there, what happens to the logic value at the output of the inverter? It is a 0. If this is a 0, what happens to the output of the NAND gate? This will go to 1 and this will go to 0, right. Now, let us trace the waveforms as to what happens when phi transitions from 0 to 1. So, this is the input clock, phi, let me call this A and let me call this B in order to help us identify the signals. So, phi, let us assume, has been 0 for a very long time prior to going up. So, if phi has been 0 for a very long time, what do you think A will look like? A will be a logical 1, and what about B? B will be a logical 0. So, this is phi, this is A and this is B. Now, when phi goes up from 0 to 1, what do you think will happen? When phi goes from 0 to 1, what happens to this NAND gate? Pardon? Okay, so the output of the inverter immediately goes to 0 because we have assumed that the inverter has got 0 delay. So, B must go high after a delay TD, very good, okay. And after B goes high and after another delay TD, what happens to A? A goes low. So, okay. Now, what happens at the falling edge? So, life continues on like this until the next edge comes, which happens here. Okay. Next, what happens? When phi goes low, A goes high after a delay TD, very good, and B goes low after another TD, and this keeps repeating itself. All right. So, this is TD and this delay is 2 TD. Does it make sense? And how do you get a non-overlapping set of signals from A and B? If you simply invert A and B, right, which I will draw in red, A bar and B bar are non-overlapping signals. Okay. So, if A goes low, B goes high only after delay TD, okay, and after B goes low, there needs to be a delay of TD before A can go high. Is this clear? One can also vary the difference between, one can vary this delay versus this delay by doing what? So, if the two NAND gates do not have equal delays, right, then you can change the non-overlapping time between B going low and A going high and make it different from the delay that there exists between A going low and B going high. Is this clear? So, this is often one of the most commonly used core circuits used to generate non-overlapping clocks. You understand? And these are in many cases deliberately made, especially when you are dealing with very low frequency signals, right. You want to be absolutely sure that the two do not overlap. When the clock rates are not very high, okay, you want to be absolutely sure that there is no overlap between these two, okay. And what you do is I mean in very fast technologies it is often very difficult to get sufficient delay in the gates, right. So, you put a chain of inverters or something in cascade, I mean this is where you deliberately want to make the gate delay slow, so that you get an appreciable non-overlap time. When you are dealing with very high speed designs, you often do not have the luxury, because if you waste significant period of the clock for non-overlap, then I mean please note that these non-overlap times are eating into the total clock period, right. During these times all the switches are open, okay. So, if you waste too much of the clock period in these non-overlap times, you are obviously reducing the amount of time you have for phi 1 being active and phi 2 being active, okay. So, in high speed designs, you know, you are often you know you try to optimize this, so that you, yes, you do want non-overlap, but you can't afford to waste a lot of that clock period just for non-overlap. In low speed designs, often if your clock rate is very low, and then it becomes very I mean you kind of get nervous when you can't see the non-overlap period on a simulator, for example, right. So, you know in a high speed design, if you are designing something at 2 gig, for example, right, the clock period is 500 picoseconds, the inverter delays are like 50 to 60 picoseconds, okay. So, if you plot phi 1 and phi 2 on a computer, you will definitely be able to see visually the non-overlap time. Now, if I suddenly reduce the clock rate to say 2 megahertz, okay, and use the same circuit, the non-overlap time will still be the same, you know, whatever you have decided, right, okay. But now your clock is 1000 times slower. So, when you plot the thing, you know, even though phi 1 and phi 2 are technically non-overlapping, okay, you can't see them anymore, and you begin to get nervous. So, a normal thing is to say, you know, if there is a lot of time and you want to be absolutely safe, you put a few more inverters and satisfy yourself that sure, even if things get skewed, finally it is not that phi 1 and phi 2 are being generated at a place and being used, they are going to be circulated to various parts of the chip, and you want to make sure that where they are needed also they remain non-overlapping. It does not make sense for you to generate phi 1 and phi 2 at one point on the chip, transport them, you know, 2 millimeters away, and then you find that because of skews the non-overlap is gone completely, you understand. So, to have some immunity to skews, you must make sure that that non-overlap time is reasonable, you understand. So, this is what is called the non-overlapping clock generator. And how do you generate phi 1 bar and phi 2 bar from this? Just use inverters, okay, and the understanding is that these are the guys which are giving you the non-overlap